Hi everyone, today we're going to talk about exponential growth and decay and the exponential growth and decay factor. First of all, in the last set of notes you learned about the exponential parent function, which was f of x equals some kind of base b to the power of x. X, our variable, is the exponent in an exponential function. Now whenever you graph it, kind of the rough sketch looked like this. This is what we call exponential growth because the graph is increasing from the left to the right. There was no vertical asymptote. This kept going up, 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 but there was a horizontal asymptote. It flattened out and it never got below y equals 0. We never had a negative number. So for the base here was always a positive number. In our example, in our notes, and the last set of notes, we used a 2. So we always have a positive base. We also never have a base of 1, because if you have a base of 1, 1 to any power, any x value is just going to be 1. And so that's not going to make for a very interesting graph. It's not going to be exponential. So our base is always positive and it's never 1, and this is what it looks like. So today we're going to talk about an exponential function as a continuous function, so it's continuing, with a variable as the exponent, like x, and is used to model growths or decays. So when you think of growth, you probably think of getting bigger. Well, that's exactly what your values are doing in an exponential growth problem. As x increases, y also increases. So your graph tends to be going up, just like that. For exponential decay, decay typically means things like decompose, take apart, go down, decrease. So decay has y values that decrease as x increases. So as x moves to the right, my y values are going to be going down. So exponential decay looks kind of like this. So they look very similar. There is a horizontal asymptote in both of these graphs. There's no vertical asymptote, but in growth, from left to right, the graph is increasing, and in decay, from left to right, the graph is decreasing. So graphically, that's kind of what it looks like. When we look at it algebraically, so with an equation, I want to mention the connection between what you see here and the parent function that we talked about yesterday, which is up here. Now, the only difference between these and what you did yesterday with the parent function is the a value. That a value right there, that a value is kind of performing a transformation on this exponential function. So just think of this as some kind of scale change for your exponential function. Now, exponential growth has your equation modeled. You can also put parentheses around the b. That might make it look a little bit nicer. But then you can also have this on the inside. So this b value, if you have exponential growth, this b value we talked about, it's not going to be 1, and it's going to be positive, but it's also going to be greater than 1. It's going to be a bigger number because you have 1 and you add some kind of rate to it, some kind of decimal. And so overall, this b value is going to be bigger than 1. It might be 1.5, 1.75, 1.02, it might be 2. So as long as b is greater than 1, then that indicates that you have exponential growth and your graph is going to look like this. So this b, this is called the growth factor. So this right here, this base, this is the growth factor. If it's greater than 1, it's a growth factor. A is the initial amount. So if you're measuring something and it is explained in an exponential growth equation, a is going to be the initial amount. And then r, this little bit that you're adding to 1 to make it a growth problem, r is the growth rate. So we're going to use this example to do one of our problems below. I'm going to kind of ignore this for right now. I'm going to move this up. There we go. I can almost fit that in the screen. Let's see. There we go. Okay. So I'm going to talk about this problem. It says identify the following parts of the exponential function. Notice that it's exponential because it has something raised to a power. So the first thing that we need to know is this growth or is this decay? Remember that growth is what occurs when you have a b-value that is bigger than 1. So look at your b-value here. Think about whether that would be the 2, the 1.25, or the 3. The b-value would be the 1.25. This is the b-value. And it is greater than 1, so that means this is exponential growth. My graph would be increasing from left to right. The initial value is the initial amount. It's the A that you see. It's what you start with, kind of like your starting point. So that initial amount here out in front, that would be 2. This is your A value. The B value was 1.25. But I need the R out of it. Now the R is the amount that you have changed from 1. So in a growth problem, the R is the amount that you add to 1 to get this growth factor. So if this is 1.25, that is 1 plus your R value. Well, you can solve this little mini equation, or you can recognize that the R value must be that extra 0.25. Because 1 plus 0.25 is the 1.25 that you see. Now the percent is a little different. The percent is the amount of change that's happening from 1. So if I take this and I convert it into a percent, 0.25 converted into a percent means that I take my decimal and I move it once, twice to the right. So this is 25%. And because this is an exponential growth problem, I say that the initial value is increasing. So it's going up, it's growing by 25%. So let's go back and let's look at a decay problem because it mirrors a lot of the growth that you see. And some of the things are called the same terms, but they're slightly different. So a decay problem looks like this on a graph. We have the same function, kind of with the scale factor being applied at the beginning. But the difference is that this b value is still positive, but it's less than 1, so it's between 0 and 1. It's some kind of fraction or decimal between 0 and 1. So the b value is less than 1, and what that implies is a decay is happening. So b is called the decay factor when it's less than 1. A is still the initial amount, it's like the starting point, and R is still should be the just rate in general. So here it's the decay rate. So let's look at our second problem. There we go. This is kind of modeled by y equals a times b to the power of x. So I need to know if this is modeling growth or decay. Well, I look at my b value. My b value is 0.25. Is that greater than 1 or between 0 and 1? 0.25 is between 0 and 1, so that means that this is exponential decay. It's less than 1. So this is my b value. The initial value is a. It's what should be out in front, and there's nothing that appears there, so I can say that this is a 1. The b value is 0.25. And because this is exponential decay, the r is embedded in here. So my b value is equal to 1 minus the rate. So what I'd like to do is think about, what do I subtract from 1 in order to get 0.25? Now you can, out to the side, solve this little miniature equation. You could subtract 1 and subtract 1. 0.25 minus 1, if you think about dollars and quarters, a quarter minus a whole dollar, that means that you're down by 75 cents. And then if you divide by the -1 to get rid of the negative sign, you get an R value of 0.75. So if you take 1 and you subtract 0.75, you end up with a B value of 0.25. So 0.75 is your R value, and the percent is what you convert into a percent from this R value, from this decimal. So 0.75 can convert to 1.275%. And were we growing or were we decaying? We were decaying. So from 1, we're going to have a decrease by 75%. Okay, so let's look at the next page. The next page asks us to classify each of the following exponential functions as either exponential growth or decay, and then fill in the other blanks. So I'm going to do number 3, and I'll do another one. Maybe I'll do number 5 or 6, but I'll definitely do number 3. So number 3, it kind of follows from y equals a times b to the power of x. I need to determine growth or decay. So I'm looking at the b value. I'm looking at whether it's more than 1 or less than 1. 1.15 is more than 1, so this is exponential growth. The initial value out in front is a 1. The b value is 1.15. The r value, the amount that I'm adding to 1 to get 1.15, is 0.15, because 1 plus 0.15 is the b value. And then the percent, if I move this twice to the right, is 15%, and it was exponential growth, so it's an increase by 15%. So perhaps now I'll move down to, number 6. So number 6, y equals a times b to the power of x is what we model from. I need to know if this is exponential growth or exponential decay, so I look at the b value. It's 0.61. Is that more or less than 1? That's less, so this is exponential decay. The initial value in front is 2. The b value is 0.61. The r value is what I get when I solve this little equation. So 0.61 equals 1 minus r. If I subtract 1, I end up with negative 0.39. And if I divide by negative 1, I get r equals 0.39. So that's my, that's my r value. You want to think about 1 minus what will give you 0.61. So you can think about money if you want. $1, I take cents away from $1 and I end up with 61 cents. How many cents do you take away from $1 to end up at 61 cents? Well, you take away 39 cents. So that's your R value here. The percent is what you get when you turn this R value into a percent. So 39%. And this was exponential decay, so it's a decrease by 39%. So I'm going to ask that you try 4 and 5 on your own. However, I do want to talk about number 5 just a minute before you complete the rest of it. So in number 5, is the b value more or less than 1? Well, it's definitely more than 1. This is exponential growth. The a value, the initial value, I'll let you do. The b value, I'll let you do. Well, actually, I'll give you the b value, so that's 2.59. However, because this is exponential growth, I need to know what the r is. What am I adding to 1 to make 2.59? And so this is a little different than the other ones, because when you subtract 1, you get an r value of 1.59. So that is your R value. And whenever you make this into a percent, you still move the decimal 2 times to the right. So this is growth, this is an increase by 159%. So more than double. So what I'd like for you to do is try the rest of number 5. We didn't write the initial value. And then I want you to also try number 4. So pause your video and see if you can get the remaining answers. So in number 4, this is exponential decay because the b value is less than 1. The initial value is 1 because there's no no coefficient out here, so we say it is 1. The b value is 0.43. The r value is what you subtract from 1 to get 0.43. So if I subtract 0.57, I get 0.43. And the percent, if I change this to a percent, this is a decay by 57%. And then in number 5, the only thing that we didn't get together was this initial value of 8. So that a value is 8 right here. We start with 8. So initial value and starting value mean the same thing. So we're going to flip to the last page of our notes today. We have 2 more examples. This at the top of the page is just to help you remember that exponential growth has a plus. So this b value is greater than 1. And exponential decay has a minus. The b value is greater than 0 but less than 1. So it's between 0 and 1. It also gives you a review on this page so that you don't have to scroll back of all of the pieces. So a is the initial or beginning value, the starting value. X is something we haven't talked about yet. X is the exponent up here. These are the units of time. It's the independent variable. It's time. So over time, if we talk about over 5 years, then x would be 5 because it is the amount of time that is passing. So x is time. Y is the ending value, so it's your resulting value, what you get. And then r is the rate, a decimal that we can change to a percent. So we've got 2 problems today to work on. Example 7 says, the world population in the year 2000 was approximately 6 billion people. The annual rate of increase was about 2%. So, some things that I notice is that the population in 2000 was approximately 6 billion. That seems to be my starting point. And then the annual rate of increase, that means growth. So increase signifies growth, was about 2%. So how do you change a percent back into a decimal? Because remember in our other problems, we changed from decimals to percents. So we moved our decimal once, twice to the right. Well, if we're given percents and we want to go back to a decimal, we want to change and move our decimal once, twice to the left. So that's what we're going to do here. When identifying the r value, I'm going to find my decimal. I'm going to move it once, twice to the left, fill in any spaces with zeros, and my r value is 0.02. Now it is growth, so that means that I am going to be adding my rate with 1. The first step says find the growth factor, that's the b value, for the world population. So the growth factor b is 1 plus the rate, because when you grow, you add. So this is 1 plus 2%, or 0.02. My growth factor is 1.02. Part B says, suppose the rate of increase continues to be 2%. Write a function, write a whole function, to model the world population growth. So I'm going to write a function that models exponential growth. Now remember, my function needs to have x's and y's, and in this case the y is going to be f of x because it did say function, so f of x equals the initial value. What was the initial value of the world population in 2000? It was 6 billion, so 6,000 million billion. There we go. There's 6 billion times my growth factor, 1 plus r, which is 1.02, raised to the power of x, which represents the time. And here we talked about an annual rate of increase, so this must be the number of years. So part C asks, what was the estimated population? So I need the population, the final answer, the result, at the end of the year 2018? Well, we started talking about the population in the year 2000. So how many years have passed from the year 2000 to 2018? Well, if I do subtraction, 2018 minus 2000, that's 18 years. That's the X value. That's how much time has passed. So what you should do is, typing into Desmos, you should find f of 18. That's 6 billion times 1.02 to the power of 18. So I've typed into Desmos 6 billion times 1.02 to the power of 18. I notice that it gives me an answer in scientific notation, and what this means is I take this number and I move the decimal to the right 9 times. So if I move it to the right 9 times, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So right here. So that answer, I'm going to write it on my paper. So I'm going to move this. That answer is 8,569,477,485 people. So that's kind of a real-world application of exponential growth. Now let's look at example 8 because it's similar, but it's just a little different. And I'm going to keep all of my pieces here so you can see them. So example 8 says a computer valued at $6,500 depreciates at a rate of 14.3% per year. So to depreciate means to go down. So this is exponential decay. And you need to know that the word depreciate means to decay. You might have seen the word appreciate, not to be thankful for, but to appreciate means to go up, to depreciate means to go down or to decay. We have what our computer was starting at, that value, and then we have the rate, which if I move to a decimal, 1, 2, that R value is that R value is 0.143 because we move that decimal twice to the left. Now I want to write a function that models the value of the computer. So here's my function f of x. It is exponential decay, so I want it to look like this. So f of x equals the starting value, which was 6,500, times 1 minus r, 1 minus r, which is 0.143, 1 minus 0.143 is 0.857. And I raise it to the power of x, the time, so per year. So there's my function that models the value of the computer. Notice that the value of the computer is going down. It's exponential decay. So it asks us to find the value of the computer after 3 years. So 3 would be the value of the time, and time is x. So 3 equals x. Remember that this value of the computer is depreciating. It's exponential decay. So I should be getting a value that's much smaller than the 6,500 that we start out with. So 6,500 times 0.857 to the power of 3. So I'm going to go into Desmos, and I'm going to type in my problem. So I have 6,500 times 0.857 to the power of 3. I get a decimal. And remember, we're talking about the value in money after 3 years. So it would make sense for money to be rounded to the nearest cent. So 2 decimal places. So this would be $4,091.25. So this would be my final amount for the computer. And it's a reasonable amount because the value of the computer is depreciating or decaying. And this answer is much lower than the initial value.